Well, it is really a great pleasure to be here in Berkeley. And I was just talking about the fact that we used to have more interaction between Berkeley and Stanford. We used to have a shuttle bus that goes between the two towers. And I really think we should find another solution, maybe a robotic boat over the bay crossing, because we really need to have more and more interaction. And I recognize the effort of Peter with the robotic symposium that brought a lot of people from Stanford over here and people from Berkeley over there, and now it's growing within the whole Bay Area. This is really fantastic. So it's really great to be here. I'm going to talk really about the fact that there is a new era in robotics that is taking us from industrial robotics, the simple robots, pick and place, moving, where the robot was inserted in the complex manufacturing process, because that process started when robots were not yet ready, to the challenge that we are taking robotics today to, and that is the human environment, the robots in the field, the robots in around many challenging areas that are going to require interaction. And interaction is something that is the most fun about robots. Our students love it. This is one example of the experimental work. This is actually class work, a project of 3 weeks, where the students are programming the robot to attack, to fight, to defend, and to perceive the humans, and doing all of it in about 3 weeks. So we should recognize that really there is possibilities of interaction. We can now do it. And what are the challenges and what are the things that we are facing in those areas? So we know the success in medical robotics, the success of now doing minimally invasive surgery, doing this by connecting the human to a robot through a haptic device that is still not using the feedback in one way, just we are using mostly vision. We are using the more haptic and maybe some more feedback with catheter technology. This is some work with from Hansen technology. There are a number of other applications where we see the human and the machine together. But really what I would like to talk about is those new challenges that we can imagine. And to talk about it, I'm going to take the example of this boat. This is archaeology underwater. And this is a boat called La Lune in French, which is the moon. And it's a 1700 boat that was returning to France and sunk off the coast of Toulon, about 20 miles off the coast, 100 meters down. So any idea about going there will prevent divers, because diving can be done at 30, 35 meters, but not, 40 meters is really the limit. And what you need to do is to build a very heavy, stiff suit where you place the human inside. And now this suit can not be operated by the human inside. Obviously, you have thrusters. It's very complex. They operate it from the boat. This is the scientific boat that is lowering now the human to that area, and this could work up to 150, 200 meters. So below, then it becomes another problem. And the question is, can't we do better? The human is there just because the human is going to be able to grasp one of those objects and put them in a container, and that would be sent up to the boat. So the problem today is that we have not only in underwater archaeology, but in coral reefs monitoring. It's really, really difficult to think about ways of going there, placing sensors, collecting samples. If we think about all the structures underwater, there are so many problems that we need to have a manual manipulation intervention that requires human divers, and it is really dangerous, challenging problem. Now, the state of the art in robotics is really fantastic in terms of the underwater observation. That is, we have underwater vehicles that can observe, that can see, that can map areas. But we have little capabilities of manipulation. I mean, we have some manipulators that are really difficult to operate. They need to be teleoperated. We don't really have the capabilities of doing like we can do on the ground, mobile manipulation. And that brought this idea of Ocean One. Ocean One is a robot that we've been building over the past 4 years. And Ocean One is a bimanual robot with hands, head. I mean, you can think about it like as a humanoid robot underwater. It doesn't have legs, but it is operated with thrusters, so it's adapted to the water. And the coolest part about it is that this robot is connected to the human. And when this robot is going to touch the bottom of the ocean, you can feel it in your hands. And that is because the concept that we are using is to connect the haptic device to this robot through fast communication that allow us to feel and interact, not to teleoperate the robot. We don't want a human to teleoperate it. It wouldn't work, because human would be very bad at creating those manipulation interaction. But a human can intervene at any moment in the system. And to do that, you can imagine a seabed village of robots connected to a station where they can get power. They can also make a connection, fast connection. Acoustic is not good for fast connection, so we use optical modem. And then to that station, optical modem is light, which is attenuated, so we have limited distance. So that station is very important to do the connection to the boat where a human is interacting. So the design was amazing in terms of complexity. We start with the bimanual manipulation, and then we find electronics, more and more things that are needed. And then we are not talking about designing a vehicle and attaching arms. We are talking about designing a whole system together, where we need really to understand the dynamics of the vehicle, which is slow, compared to the dynamics of the arms that is faster, and design a macro mini structure that allow us to build those capabilities for dynamic control and operations underwater. Fabrication, we've been lucky to have the help of Meka Robotics with the arms, but we had to redesign the whole arms together with them. And we had also to build all the electronics. I mean, the students worked for years on this project, building the body of the robot, assembling, putting many different things. The first tests of the robot were done in July, and in August, end of August, we were operating the vehicle itself, and the robot was moving with all the electronics without frying underwater, which was a milestone. The aim was to get the robot ready for actually IRIS. If I recall, it was 29th of September. And IRIS was a challenge for us because the robot arms arrived on the 24th. And very quickly, in a few days, we assembled the robot, put it in the water, and for the 29th, and we were able to connect Hamburg to Stanford. So the robot was at Stanford, and we started the initial interaction from Hamburg all the way back to Stanford. So this is just to give you an idea about one example of one challenging environment. Why can't we do the same thing for mining? I mean, how many accidents in mining we have? Can't we replace a worker in the mines? I really believe it's possible. It's not going to be completely autonomous. It will be a very complex environment, many difficult tasks. We will need still the skills of the human, and we might be able to connect the human, placing the human, extracting the human physically from the dangerous area, and placing the human where the human is safe, but still able to operate a robot that is placed inside the mine. The same thing for geologists. These areas are the most dangerous areas. They are just opened, and we are sending human there. We think about high altitude stations. We cannot leave human there, and operating the stations is very, very difficult. So can't we place robots that somehow are connected to human, and human can operate them or intervene when there is help that is needed? So we saw in the past years a lot of progress in mobility. Robotic mobility has been really amazing. I mean, in terms of all the new capabilities that we are seeing, from flying robots to smart vehicles to underwater vehicles, all of those progress are bringing that capability. But what is still missing is the manipulation ability to be combined with mobility. So going beyond mobility, we really have to think about the integration of those two capabilities. And I have the example of Ashimo here. Ashimo was studying at Stanford and failed for many years, so we kept him for 12 years at Stanford before graduating Ashimo. And the reason we wanted to teach Ashimo something more was that if you really want to interact with the world with a robot, a humanoid robot, you are going to need to integrate the capability of manipulation and the capabilities of mobility in one integrated system. So the mechanism appears to bring this capability. We can see it is possible. The question we need to ask ourselves is how much programming goes into this. Essentially, Honda goes by moving and teaching every joint motion, integrating them all together to create this behavior. And if we change the location of anything, we have to reprogram again. So how come a little child can do it? And Peter has an answer to that, right? I mean, we have skills, and we have a process that goes, and we don't think about it. I mean, it is going to be almost automatic if we acquire this process and bring it to human. So programming was used and was fine as long as we were doing over and over and over the same task. In industrial robotics, that was fine. We spent a lot of money. The most expensive part of automation is building the assembly line and programming the assembly line, which makes it very difficult for small companies to have assembly lines. And but basically it works once we put all the fixtures, the jigs, and integrate the robot to do the simple task. Now, if we are talking seriously about taking robots in those environments, well, then we really better think about it again and see how this can be done. We cannot anymore go and program at the lowest level of the robot. We would like to acquire skills, but we would like those skills to be encoded in ways where now we can plan with higher level skills and behavior that the robot can use, and then also connect the human to those behaviors. So as much as we need the robots also need us. And one of the basic interaction you can think about is, here is the haptic device interacting with the robot. So typically we interact with a virtual environment. Now we go all the way to the physical environment. When we touch, we feel it. But this is a way to teach the robot to interact with the robot and also to feel what the robot is doing in action. Now, this concept is now taken underwater, and it's concept with more sophisticated haptic device that has 6 degrees of freedom, and the robot now is diving, and we are in the environment of the water, and we interact. But this is our first stage where we are going to be able to, in fact, design our robot before even building it. So the idea is, when we're going to develop a robot, it is the wrong thing to think a human can teleoperate contact. They will crash the robot. And I have this experience a long time ago with Tecnomare in Italy, where operators were supposed to do some inspection underwater through teleoperation. It was so difficult for them. And as soon as we placed a few force sensors, tactile sensors on the robot, just like they push, and the robot will adapt to the environment and make the contact and co-locate the sensors with the control, with everything, and get that stability. So we really need to build those advanced skills on the robot to operate and let the human intervene when there is a difficult, challenging problem. So there are many features about how to get there, and I'm going very quickly to go over some of the things before showing you some of the results. So manipulation skills. Humans are amazing at it. How can we get them to robots? Well, I really would like to see, first of all, capabilities that are general. And in order to generalize, we need to understand this skill and from the human and map it to the robot. Robot and human are different. Human use forward prediction, robots use feedback. One of the key feedback is force control and compliant motion control. Here what you see is something that is done without any programming of trajectories. It's based on the contact information that is guiding the motion. From any initial condition with the same program, the contact forces are guiding the motion to achieve this behavior. Well, this relies on a capability called torque control. Unless we have torque control on the robot, unless we are able to control remove the actuation, remove the gears, and make the robot compliant, fully compliant, it's going to be very difficult to implement any of those techniques. So this is one of the things that we were missing for many years. And the reason was most robots were designed for industrial robotics, where you are dealing with the position control, you're programming ahead of time, everything. So this is a capability that is essential for dynamics, essential for compliance, and for everything else. In fact, in the mid-90s, we built the first torque-controlled robot. And you can see one part of it over here. And this is aerodynamic ping pong that is done by just blowing on the robot to show you the level of performance that you can achieve just by using proper control. We've been spending so much effort fighting with the robots rather than really using those robots. In fact, this technology was completed by DLR and led to the KUKA robot, which uses the same technology of torque control. Now, once we have torque control and force sensing and force control, then we can measure this force at the contact. And if we measure this force at the contact, we can resolve it as a moment about a centroid that is related to the geometry. And now this centroid is going to allow us, centroid of compliance, allow us to perform the motion. So we can conduct those experiments with the human, and now we can ask the human and record forces and motion of the human. And the objective here is to be able to generalize around one behavior. This is just one example of one behavior. And now the generalization of it, now this is mapped to the robot over different geometries, different material, different grasping locations. And the robot is able to do it. Even if we disturb the position where the robot is grasping, the task is still performed, and the compliant motion is going to lead, even if we disturb even the robot itself. So now this simple primitive that we have can be combined with other primitives through transitions. And this is an example of how this could be applied. This is a small part of the 787 Boeing wing, where the robot is supposed to place this object there. And these are several primitives that are being executed, and there are transitions between them, and we disturb the robot every time, and the robot execute the program to reach that configuration. So this type of robustness is coming from our understanding of how we are able now to perform those compliant motion primitives reliably and capture also a whole program for executing a more complex behavior. If we want the robot to interact with the human, well, the human interact with the robot, we need to model human. And it turned out that robotics provides amazing tools, algorithms, to efficiently model human. In fact, by looking and integrating the muscles, we are able to look also at the characteristics that inspire our way of controlling humanoid robots. So those characteristics relate to how we posture the body when we are exerting a force. And this is an example of those characteristics that we found. That is, if you think about pushing a heavy object, you wouldn't do it this way because all the muscles will need to support it. And if you look at the effort exerted by all the muscles, it would be huge. Whereas in here, the body is taking that reaction force through the bones, and the muscles are not doing any support. In fact, you need then to have subject-specific modeling of those muscles. And we have been working, in fact, in collaboration with the group of Regina they see here in building muscles, subject-specific muscle models through MRI, and there is fantastic results in that area. So now, if we have that, then we can go to each of the subject and analyze the motion and look. This is actually a Stanford athlete that was injured by maybe a Cal athlete, I don't know. And we've been, now we're constructing the motion, and then we are going to be able to analyze that motion and then prescribe exercises, or we are looking at high performance motion, and then we are going to prescribe how to improve performance. Anyone here play tennis? Okay, tennis. Would you need, yeah, would you need some help? Do you need any help with improving your tennis, or we're fine? We discovered the secret, actually, you know. There is something about how you look at the capacity of your muscle, your posture, and how you determine the capacity of the tip to accelerate. And that is really subject-specific. Very often we imitate. Imitating is not a good idea. So there is a specific characteristic for every subject, and we can trace your lines of acceleration and how to build momentum for every subject in a very distinct way from others. And well, this is a very, very interesting topic, but this is now applying robotics to human. In fact, we are pursuing another project where we are taking haptics to create a task meaningful environment inside MRI, so that we can, in fact, look at activity in the brain, so to understand how humans represent tasks, and then connect that to physiology by looking at the forces and the motion. And this is actually the device which now is extended to have 6 degrees of freedom. And that is allowing us to combine for the first time both activities and do those activities in a meaningful way. That is, we do more complex behavior, because inside the MRI you are confined. You cannot do too much. And here you can, through the haptics, stimulate the brain to do much more complex tasks. Another problem, we talk about compliance. So this is really exciting, but compliance is not only about one-point contact. It's about the fact that your robot is going to touch at multiple points, and this is always the case in any complex task. You're going to brace, you're going to reach, you're going to apply specific forces, and you're going to have reaction forces. One thing that the community has forgotten about those multi-contact is the fact that anytime you have 2 contacts, you create internal forces in addition to the resulting forces. And if you forget about your internal forces, you go unbalanced. No wonder DRC, I mean, we have a lot of problems where just push, it doesn't, unless you really model your internal forces. So you need a model. We introduce a model called the virtual linkage that capture all the internal forces, resulting forces, and that allows us now to implement compliance at multiple points, and that is going to take us now to putting one component of the control, because contact is one aspect. You have the posture, you have the task, motion, you have all the contact, you have collision, self-collision, you have obstacles, what else? Balance. Okay, how can we do this? This is really challenging. I mean, now the problem is we have to do this in real time. And to do this in real time means, I mean, we have the tools. We can take all this problem and map it to configuration space, map our obstacles, and do an optimization in C space and try to do it. Obviously, it will take hours to come up with a solution, and as soon as we start moving, we're going to discover that we need to redo it again. We change contact, or we change the environment, or we discover new obstacle, and everything needs to be redone. So to do this in real time online, there is really a key model for us, and this is the human. I mean, human actually never resolved the whole problem with it as a complete problem. We focus on the task. We assume that we have the ability to control our posture and adapt it to where the task is going. We have separate controllers that are handling all these different things. So constraints can be handled if we control them. Artificial potential field is one way of combining repulsive and attractive fields to basically achieve collision avoidance while reaching the goal. But essentially, you are not anymore looking at constraints, because you are taking the artificial potential field and integrating it inside the objective function. We are going to do the same thing over all these different things, but we are going to do them in a way where everything is going to be compatible. So to do that, we start with the task. So once we have the task, we say we want to deal with the posture control, the motion control here in the contact, but we have all these constraints. Now the problem is, if you look at this as descriptions in terms of coordinate, X, Y, Z, orientations, whatever, you have a lot of dependencies between them. So what we do is we produce a sort of prioritized representation that capture those constraints, that make use of their representation to go to null spaces and make projections and produce a set of coordinates that essentially lead us to those set of generalized coordinates that we can control and that are compatible with the task, with the constraints, with the objective that we have. And once we have a set of coordinates, we have a Jacobian. And once we have a Jacobian, it's really, really important, because we can take our dynamics and project it in that space. And now we can go to that space. Don't worry about the equations. Basically, this is the generic way of representing the dynamics. Now we have, in that specific description, task, constraints, we have the dynamics in that space. And once we have that dynamics, we can immediately decouple the dynamics through a standard control structure, nonlinear dynamic decoupling, that allow us now to control the robot. So, but we're in the proper space with all the constraints, through a gradient descent that is taking care of all these different things in real time. So one thing about humanoid robots, if you approach them, people are really scared. Like if you go to a show of Ashimo, they tell you there is one rule with Ashimo: don't touch it. Because if you touch the robot, you create reaction forces, and immediately you interrupt the trajectory, and the robot will fall. And we with our robot, we just broken that rule. Now the robot is guided by your hands. It is feeling your force and is going in the direction you're guiding the robot. It's making contact without bouncing. There is no trajectories to talk about. It is behaviors that are controlling the posture of the robot, controlling its motion, controlling its contact. Now we tell the robot, okay, don't touch my hand, all right? And the robot sees your hand and creates the repulsive force, and it moves away from your hand. Now, if we start to think why we cannot take these today and replace this worker in Fukushima by a humanoid robot, what is the problem? Well, the problem is most humanoid robots were designed with controllers that use ZMP, zero moment point, that assume flat indoor environment, basically. And if you're in a flat environment controller and you go out in 3 dimensions, it's going to fail. In addition to the fact that you're going to have to deal with a lot of different points of compliance. So the first thing we are going to do is to take our models and say, we're going to move like human using the environment, using contact. So using contact means we're going to make use of surfaces that are slippery, so we need to model the friction. And if we model the friction and model the dynamics, now the robot is capable of making contact, putting all the reaction forces inside the cone of friction so you do not slip, and then deal with the dynamic and the fact that all these contacts are moving. This is really remarkable, but if you want to be more surprised, I can show you something even more challenging. In climbing, you really don't like slippery surfaces. I mean, it is not really a good thing. Okay, so we're going to take HRP 4C and put a slippery surface, and now you can see immediately the balance is, this balance is very, very difficult for the robot unless you have the proper models to distribute the forces for this under-actuated robot, because you're still missing 6 motors, right? It's not connected to the ground. So this idea is the beginning of thinking, okay, what else humans do to move in those challenging environments? Well, we use tools to balance. So why don't we extend the capability of the robot, go from biped to triped to quadruped to supraped? Any number of contacts now you can support your robot. And now with this, you have a sensor that you are probing the environment with. You increase your support area, and then you have you look, you plan some potential location, you check them out every step, and then you decide, okay, the next one is feasible or not feasible, and you make your selection. But obviously, you need to modify your selection because the environment is always changing. You discover new things in the environment. So we take our plan, and this is something we worked on within mobile manipulation, is to create an elastic plan that deforms as, so you take the plan and treat it like a physical object, like an elastic, that is deforming through your sensory feedback, and we can, in a few seconds, replan everything without having to actually run a planning algorithm. Now, we apply all of these to a real robot, and we go back to our Red Sea Robotic Exploratorium. That was the initial project that Stanford started with KAUST and Meka, and that was aimed really at the coral reef environment, replacing human there. So the aim was collecting samples. They always have a lot of trouble collecting samples in the Red Sea, and there are huge areas to cover, and they don't have people who can do that. And the challenge was really not to think about it like, okay, let's buy a underwater vehicle, attach a few arms. I mean, the Schilling makes very nice arms. You can attach the arms, and you're done. In fact, the problem was how to design a machine that is going to take advantage of the fact that your electrical arms are faster. Your body is using thrusters, it's very slow. And if you just try to use the thruster to stop and dock here, you will break it. Notice how the arms are bending. The arms are bending to take the inertia of the slow dynamics of the body. And this was a large part of the design. When we designed the robot, we work at with a workspace where we can compensate for the slow dynamics of the. Could you open the door for Ken? So you need to deal with that aspect of the dynamics and accelerate the response of the system through something we call the reduced effective inertia and the macro-mini dynamic coordination. So this was part of the design. When we designed the robot, it was to achieve those characteristics, so you couldn't just like buy pieces and put it together and build a robot that is from a vehicle with, so this is an arm, head, body system that is integrated. The other thing is this robot is going to receive help from the human, so we need to be able to build an interface that the human can use, so you can program different behavior and you can remember them, but you are also able to intervene haptically with the robot. So now the robot is moving underwater. This is a simulation, dynamic simulation in the water environment, And here the robot is going to, so you have multiple views. You have view from the bottom of the robot. When you are going to catch, I'm going to accelerate this a little bit. So now you catch the object, you take it, you place it, and then you go next to find the treasure. The pirate left, and then you change the view, and then, so this environment is called Psi, and this environment allows us to simulate contact and produce physical behavior, and also produce all the characteristics of the robot. So one thing about when you are grasping something, we need to also remember is, let me show it maybe in this context. When you look at your dynamic at each of the arms, you have properties of the effective masses in different directions. So when the arm is extended, the mass is very big. And if you touch any object, when the mass is extended, you produce large inertia. So you have to be very careful when you're approaching an object that has some mass. When you bring them together, actually you are adding them. So you have a transition, discrete transition between a small mass you're handling to a large mass, and that makes it very, very important to integrate that dynamics in your model. This is exactly what happens with human. I mean, if you are running to a wall, you don't do like this, you will break your arms. You have to go to a configuration where the arms have smaller impact forces. And those configurations are when you are in the proper workspace of the robot. So now we bring multiple robots together. Those characteristics need to be integrated in the system. You need to make sure your robot is robust. So if we apply, at the tail, we're going to apply a large force. You see what is happening. The posture is changing, the task remains. And this is how you are building those priorities. You're saying, my task needs to be achieved. I can modify, I can let the posture have a lower priority, and then the robot is going to integrate that directly in the control system. When they come together, you are going to have augmented object for the first robot, the second robot, and all of these will be combined as a system of augmented object with the model of the virtual linkage that allow us to control that interaction and deal even with those disturbances. Okay, let's go to the pool. So now we take the robot and we have this interface allowing us to control the arms, the body in different mode, the haptics, to integrate the skills. All of this very simple. This is the operator, and basically you have access also to the haptic device to feel what the robot, where the robot is stuck, what is the robot is touching, what kind of characteristics you have. We were talking with Ken earlier this morning. I said it is like surgery underwater, basically. You're going to surgery underwater. So about a month ago, February 9th, we managed to get all the pieces together, and here you see the robot in the water. This is at Stanford pool, and the robot is given a set of key points, and basically the robot is moving, and the operator is monitoring the motion. The robot is autonomous and it has its own battery, but for the test we use our pedals. And the coolest part about this is that while the robot is swimming, look who's swimming next to it. I mean, it is like normal. We have robots in the pool, that's fine. So once you want to touch the bottom, you can touch it, and you're now reflecting this with the first sensor back to the haptic device, and you are going to feel that force on the robot. And in fact, all of this is I mean, this is an implementation of that architecture as one example of all the different robots that you can have. I mean, it doesn't matter, it's underwater, it's climbing or underground. So what is in here is, as you know, this is the line of action over here. This is the line of perception. And what is critical for the robot to operate in real time is to deal with the constraints, with everything in real time. And this needs to be running at kilohertz, very fast. And while you are dealing with all your local constraints, obstacles, self-collision, dynamics, everything. But then you continue to process the information, you extract features, and now you can start to use your primitives. Your planning is done with primitives, assuming that you have uncertainties and errors, and you're not going to commit to a specific location in space. It will depend on your skills and ability that you built in your primitive level. But if your plan is failing, immediately your elastic plan is adjusting. And so we go from 1 kilohertz to 100 hertz to 10 hertz, and then to minutes in the planning. But at any level, the human can intervene through this visual and haptic interaction. So yesterday I get the design of the new head, because right now this is going to be arriving today. When I get back to Stanford, I probably see it. It's really cool. Yeah, I was going to say, I mean, this architecture is, yes, we're showing it here in the ocean. We showed it in climbing, but you can apply it in surgery. You can apply it for humanoid robot underground, in any in field application. These were one of the few students during those latest tests, but many people were involved in this. Thank you very much for your attention. Right. And with the, I mean, if you do, I said, if you do a complete plan of a robot with 730 degrees of freedom to make multiple contact among obstacles in configuration space, it is really exponential in the number of degrees of freedom. I mean, we do it now. No. I mean, collision avoidance. I mean, you need to build your C obstacles. I mean, if you do the complete conventional way, it is really complex still. I mean, now we use randomized motion planning. We sample. We never reconstruct the space. But if you reconstruct, that's why we stopped reconstructing the full C space. And that assumption that we used to have in the past about, okay, let's be complete and plan everything in details and then move one step. Oh no, I have to replan again. I mean, this is the idea that human plan with feasible actions. I mean, we roughly plan the motion in space. We know those actions are feasible, and then in real time we are adjusting to the actual sensing and our location and unpredicted obstacles. And that is the idea, that we can separate by building capabilities at the lowest level to take into account your self-collision, your joint limits, your local obstacles, and then planning something that is making the assumption that, yes, you're going to fail because you will find obstacles, so you have to deal with it. So you're not planning the complete motion every time. I mean, that is the idea of this structure. Yes? Mm-hmm. Right. Yeah, that's what you missed when you were you were outside. So yeah, that's fine. I talked about how we build primitives here by observing the human, not only motion, but essentially forces, and how can we, in fact, remove the motion trajectories and just focus on the interaction itself, and then abstract this to a representation that uses, I mean, basically we extract a strategy rather than trajectories and specific data. So the human now is learning a strategy. And in the case, anyone has a phone here? Yeah, maybe I have a phone, yeah. All right, so this, one of the strategy I was illustrating is the fact that if you are taking this and trying to make contact, if you make this contact, it's amazing. You're going to rotate in this direction. If you touch here first, you rotate in this direction. If you touch there, you rotate in the... Why? Well, there is a centroid that is going to be the centroid of compliance. But abstracting your learning to that level, now you are learning that strategy, and then you go and implement it in the proper way with the capability of the robot that are different from the capability of human. We should never just take data from human and map it directly to the robot because they are different. Robots can do feedback. They can sense better the torque and the forces, and whereas humans are relying much more on prediction. And humans are amazing, I mean, at their skills, but we can, with machines, we can do and implement those strategies. Sometimes the strategies are not the same. That's why you need planning in those actions. But learning is so important. I mean, it's so critical to be applied. I mean, so much. Once you dealt with those task level dynamics and control and constraints, everything in contact is going to be here. And how you handle that is going to rely on observing human skills, mapping them, abstracting them, representing them, and then implementing them on the robot system. Yeah.
What do you think are some of the mental challenges? This all seems to work very well, right? But then what's next? I don't think there's a good feel for what you're thinking is next.
Yeah, I think we are, I mean, now in the heart here. I think we really have how perception is going to allow us to invoke for a given plan the proper strategies to be used, encoded in the plan. I mean, the truth of the matter in robotics, very often we go to our own PhD work and we take a methodology and then we say, oh, this is fantastic, and it's true. I mean, this is great. Potential field was fantastic. Then take that methodology and try to push it, keep pushing, keep pushing. So our colleague Kodicek said, okay, it will solve everything. And we keep pushing it as if this method is going to solve the whole problem. And I really think it is very important to realize that there is multi-scale times that a system here, we need real time here, but here it is much slower. These are input to the dynamical system. And even ahead, I mean, as we move up, there might be multiple levels. So I really think learning is going to be essential. I really think perception is going to be very, very important. And I really think the connection with the planning and how we plan, how we now modify our thinking about planning is going to be very important. If we keep talking about every time we have to recompute that plan, it is a waste of time. And this is what most of the time we are doing, especially in manipulation. We should also remove ourselves from the challenge of thinking in trajectories. We need to go to contact space and look at not only the motion, but really the normals and analyze all these interactions. We need also to look here on the mechanisms designs. I mean, this is happening today. We have so many amazing development that can change the robot. And as I said earlier, we spent, I mean, you know, how much time we wasted just fighting with the robot. Just this robot cannot get to the bandwidth. I mean, before it was like issues of computing power, etc. But but beyond that, all the limitations, non-bike drivable robots, you are forced to program the joint motions, you are forced to do inverse kinematics, you forget the whole problem. Yeah. No, but it's the wrong, yeah, exactly. I mean, but it is wrong. Redesign your robot, make your robot lightweight, efficient to interact, and then the control becomes so simple. And don't think about who cares about what this joint is doing with respect. What I need is the task and understand the dynamic at the task, and then okay, that part is maybe almost going to be done. But then how to move further, build those capabilities and skills, I think that is where the problem. And I know here in this place, we have people who have been and are working and contributing to this, so it's really great. But this is the challenge, I think, both side perception and the action side.
I have a couple of questions. So one you mentioned that teleoperation wouldn't work. Second question is, unless I miss something, the tactile sensing in your robot hands is enormously impoverished compared to humans.
Yeah. Well.
Why do you think we have so much tactile sensing in your hands? What is it that the robot can't do?
Yeah. So actually, the first question, try to I don't know, to turn off the light with just one long cane. I mean, just like try to, the control, when you are far away from something and you don't have the closed loop and the feedback, it's really hard. Now, teleoperation through visual feedback with some kind of like observation, trying to move your master's robot to control the slave robot somewhere else. I mean, that's where robotics started, and that is where it started with nuclear power plants, where we couldn't go inside, and we would use actually the same dynamic. I mean, same kinematics, same robot. We move one, the other one would follow. And human who have tried to work with those robots had really a lot of difficulties stabilizing those contacts. I mean, when you start to have a dynamical system and you are different from the robot, then you have difficulties. You get basically like bouncing, and you get all kind of I mean, there are different dynamics. Now, you can reduce the characteristics, you can do passivity control, you can do some of those things. But when it becomes complex with multi-contact, as I showed, it becomes really difficult. So I believe we need autonomy, local autonomy to do the contact. And we know how to do it. It is, I mean, even on myself, on a human, climbing with those conditions of slippery surfaces and things like that, it's really hard. So let the robot handle all these different degrees of freedom in its own way. I really agree with you that we are not using the tactile perception as we can. We have made in the last 5 years amazing progress. The new material fabrication, the integration, the mechatronics, the new method of putting things together are leading to fantastic new tactile perception devices in hands. And so at IIT, in Italian Institute of Technology, you saw their tactile sensors are really beautiful. I mean, here and in several other places, I think tactile perception is and tactile sensing is becoming commercial. At Stanford, with the group of Katkowski, we have like miniature tactile sensors that goes in the finger, the tip of the finger. Right now, we are building array of visual sensing that can be integrated in the hand or the feet. I mean, we are going to see much more integration of sensors in the body of the robot. And this is what is going to change things. But it's very, very important. I agree. Yes, one more question.
I'm curious what you think about, so if you learn the way operated policy
Yeah, yeah, yeah. You need no. I mean, I agree. I mean, I'm not saying. If we can learn from the human skills, this is great. If we can encode skills directly from planning, but what I'm saying is, let's stop planning specific joint motions that have nothing to do with the final task, and let's do it as a skill, and let's build that skill using the contact information and using the tactile information and using all the different things that are really essential, not really the trajectory that is going always to fail. All right, it was wonderful to be here. Thank you for organizing everything. Thank you. Thank you.